types of grazing. I won't go through them, but all of these types of grazing is what this grazing algorithm is meant to be able to detect. So following this piece of context, this is the presentation structure. I'll start with the problem statement, then the data and methodology, the model design to detect grazing, followed by the output, the results and statistics, and then the room for improvements for this project. So the main problem statement for this case study is to answer the question if a certain parcel has been grazed over the past year. So far, exclusively Sentinel-1 is being used to detect grazing because, as I said earlier, you can look through clouds. Ideally, of course, you would like to use Sentinel-2 because grazing is much easier seen optically than through a radar. But this is not possible because of the clouds. After doing a literature study, it did appear like grazing detection is possible using Sentinel-1 because you've got coherence, which is meant to increase after a grazing event, and backscatter, which is meant to increase after a grazing event. This is all due to the grass height, as both of these signals increase as the grass height decreases. And so that's how you would detect grazing. Some challenges noted from the literature study was that grazing is just very difficult to detect using Sentinel-1 because the signal is very noisy. There are some very nonlinear relationships between the signals and grazing, which is why deep learning is perfect, as it can pick up on those nonlinear relationships between the signals and grazing events. So now the data used for this project, this is an overview of the open source data use. So Python is used to build the model pipeline. QGIS is used for visualization of the parcels, for example, and that's also how the grazing observations come in. Sen4cap is used to compute or to retrieve signals. The types of signals used is Sentinel-1 time series, and the labels, or I will call them labels, they are daily grazing observations. They are the only part of this list which is not open source, but they are crucial for this project because you need these observations. So moving on to Sen4cap, they are part of the signal retrieval part of the project. It's an ESA project which aims to provide stakeholders, such as myself in this case, with Sentinel-1 and Sentinel-2 information. It's fully open source. It is a bit complicated at first how to use it. In very short terms, you upload a shapefile of parcels. You give the date range of when you want data, what type of data you want, and then it retrieves it for you over a very lengthy process. The signal and label data used for this project up to now is 2022 grazing data, to which you need signal data for the same time period. So I've chosen Sentinel-1A data between March 1st to November 30th. Note that this is only Sentinel-1A. Sentinel-1B has been offline since start of 2021, I think. And so there's no data from there. But from the Sentinel-1A data between March 1st and November 30th, do you see my mouse? Yes. These three signals have been, have been retrieved, from which the later three signals have been derived. The last three signals are basically are just derivations of the first three signals. The label data used are daily grazing observations from 2022 of very well maintained grassland parcels. So they can be seen sort of as the ideal training set because the observations are daily, they're very consistent, and it's on perfect grasslands really. You see here a overview on what the signals look like in relation to grazing observations, from which you can see that there's no real linear relationship between observations and the signals. The literature suggested that coherence and the grazing observations had a very strong correlation, But here you see coherence in blue, which is meant to increase after a grazing event. Here it's true, but here you see a very sharp decrease in coherence, even though there's been grazing, followed by this one as well, showing that there is more to it than just coherence. The general workflow of the grazing marker. You start on the left side and move to the right. So you've got the Sentinel-1 signals along with the grazing observations. You do some pre-processing to it, like deriving those last three indices that I mentioned just now for the signals. The grazing observations, you have to match the dates of the observations to the Sentinel-1 passes, after which it is passed on to what I'd like to call the CNN block, so the convolutional neural network block. Really what it is, it's 5 different convolutional neural networks, which are each trained separately to produce separate results, which come in the form of a probability. So a probability between 0 and 1, where 0 is not grazed and 1 is grazed. So you could have, for example, a value of 0.6, which will be considered grazed, whereas a value of 0.3 will be considered not grazed. These 5 outputs are averaged to get an average probability, to which this threshold is applied. So if the probability is above 0.5, it gets a label of 1, and vice versa. What this looks like in the results, it's a bit vague for the people sitting at the back maybe, but it's also color-coded. Everything in blue signifies, so just here in the top rectangle, everything in blue are the low probabilities, whereas the red are the higher probabilities. You see here, for example, where the mouse is a 0.88 probability, which translates to a 1, which is a grazing prediction. So the middle one is the predicted, and the bottom one is the testing set. If you look closely, you will see that some of the predictions do correspond with the testing set, not all of them. The grazing marker up to now is, let's say, pessimistic. It focuses more on precision than recall. So when it predicts a grazing event, it means that there usually has been a grazing event, rather than being optimistic and predicting too many grazing events compared to what is actually there. So here's a brief overview of the results. The objective of the grazing marker was to determine whether or not a certain parcel has been grazed at least once over the year. So what you do is you aggregate, or on the x-axis here, you have timestamp. On the y-axis here, you've got the number of parcels. You aggregate everything on the x-axis, and you see if there's been at least one, it means that there's been a grazing event. If you look at only those statistics, you get these. Well, if you look at only those results, you get these statistics with a tested on different testing sets. Testing set 1 had the same type of grazing observations as the training set, giving it, or which resulted in very high precision recall in F1. Testing set 2 included not only intensive grazing, but also extensive grazing cases on different types of grassland pastures. So not only the ones in perfect conditions, which had been used in the training set, which resulted in a lower precision and recall. And then tested on both resulted in an even lower precision and recall, which may signify that the training set needs to be increased to include more diverse types of grasslands. From the confusion matrices, just they show basically what the precision and recall stats are made of. However, digging deeper into the results, you see that the event level statistics, which are getting the date right of a grazing event, they show a much larger decrease in precision and recall. This is because it's very difficult to get the exact date right. For example, so Sentinel-1 has got a 12-day revisit time. It's very difficult from that to determine exactly which day a grazing event has taken place. It gets it right nearly 50% of the time. The highest probability grazing event does usually correspond to an actual grazing event, but the lower probability grazing events, well, they have a lower probability and are more or more incorrect, let's say. Improvements can obviously be made then to the event level statistics, so getting the date right. I'd just like to name these four. There are more ways, of course. The first one's hyperparameter optimization, which I will not go into in detail, but that's basically getting the hyperparameters for the convolutional neural network right. After that, increasing the information from the signals. So now it's Sentinel-1, which is very noisy. How can you get more information from that? Then creating a pre-marker grassland classification. And lastly, including more training data. So I'll start with increasing information from the signals. You can have feature selection, which is basically, or which can be seen as getting rid of one of the signals. Say, for example, if you recall from here, say, for example, that one of these signals is really providing more noise than information. You should get rid of it so that the model will be able to perform better. Next is a pixel-based classification. What's being done now is that the mean signals for an entire parcel are taken, and like that, a grazing prediction is made. Whereas I think it can be improved if you just do it pixel by pixel. So say, for example, you've got a 1,000 square meter grassland parcel. If only in one corner of that parcel there's been grazing, it will be more difficult to detect using the method I'm doing now. So by taking the mean signal of the parcel rather than pixel by pixel. Because you would be able to see that just one pixel is being grazed intensively, which would mean that the whole parcel will get a label of 1. Next is a deep learning way to link Sentinel-1 backscatter values to NDVI. NDVI is a normalized difference vegetation index, which basically indicates how green, or among other things, how green a plant is. Grass loses its greenness after grazing events, which means that it can be used for grazing detection. There have been studies which have been able to do this. I'm in the process of trying to work it out on how to relate the backscatter values from Sentinel-1 to NDVI. I propose using a convolutional neural network to do this classification task as well, but of course, other ways, other methods to do this are available. Next is a pre-marker grassland classification, which is basically for the marker to have a sort of a knowledge of what type of grassland it's trying to classify as grazing or not grazing. Because should the marker really be picking up grazing in a parcel like on the right, ideally the parcel or the parcels on the right should be given a lower weighting than the parcels here on the left. It's much more likely that grazing will occur on the parcel on the left rather than on the right. Increasing the amount of training data. In most machine learning experiments, increasing the amount of training data, if it's accurate, of course, will yield better results. For example, in this case, I could use more training years in the training set. Including weather events would hopefully increase the results a lot because precipitation and drought affects radar signals. Precipitation will decrease the backscatter, whereas drought will increase it. It also affects the probability that livestock will go out to graze. If it's been raining a lot, a farmer will not want his livestock out because it will damage the grass too much. These would all be important factors for the classification model. Lastly is increasing the spatial variability of the data. With this, I don't only mean geographically, but also geologically. So on very hilly terrain, for example, I don't have any training data at the moment. And it would be ideal if the training data is more spread out across the country. There's already some spatial variability. Like the training sets are across the entire country, but not quite in the reach I'd like it to be. The location transferability is usually low in machine learning experiments. If you train it on one area and then test it on another one, the results do usually decrease. Some issues regarding this project which aren't really fixable is that one of the Sentinel-1 satellites is offline. So yeah, it's got a 12-day temporal resolution now, which poses a big issue if grazing has been recorded on or if there's been a grazing event on the 13th day, because grass will grow back in the following 11 days, and there's no way you can pick it up. The radar signal is very noisy, as you saw from the graph I showed earlier with the grazing observations. There's a very nonlinear relationship between grazing and the signals. And it's nearly impossible to detect very extensive grazing. If you ideally you would be able to, or you should be able to detect one cow grazing in the field, but that's impossible unless you use a VHR imagery, I suppose. That concludes my presentation. If there are any questions, let me know.
Perfect time. Thank you. So very interesting talk. Very novel application and use of central data. So maybe some questions for Adrian?
Can you talk a little bit about the data pipeline, the central usually depending
from Central Cap, for example?
Yeah, from the server to actually processing. Maybe share some learnings that you.
How? So you mean from Central Cap, for example?
How do you download the Sentinel data? How is it processed, and how do you run the model against it?
How it's working now? Obviously, I'm not working alone on this. The data retrieval part is not done by me personally. But how it works is I have a shapefile of the training, or where I've got grazing observations, right? From QGIS, so these parcels, for example. These shapefiles are just part of one zip file, which also contains configuration file, crop codes. Those are
and it's really nice to sort of have you guys here. What I want to do today is talk a little bit about geodesign. I know for a lot of you, it's a new topic, so I want to give you a little bit of an introduction. And then I'm going to share with you some of the recent work that we are doing as far as sprawl indicators, which ties in nicely with Kevin's work as well. So Geodesign Hub, by the way, is an SME, a small company in Ireland. We are in Harcourt Street in Dublin. If any of this interests you, you're very welcome to drop by at the office, lunch, whatever, coffee. I can go over some of these. So as I said, we start with a brief introduction for geodesign. The way I think about this is that all the data, GIS, all of the analysis that you do happen on observations in the past when some satellite sends something, some sensor sends something. If you're lucky, you can do real-time observations and so on. And geodesign deals with the future. So if you think of GIS deals with past or real-time data analysis, geodesign deals with the future. Then the question becomes whose future? And in a sort of a democratic society, it obviously is everyone's future. And then when you start to make decisions on these futures for people, engagement is very important. And essentially, when you're trying to engage, there will inevitably be conflicts and disagreements. And normal response to engagement is either a checkbox list, or you just do it for the namesake and so on. But what geodesign offers is digital negotiation capabilities to handle conflicts and disagreements. So essentially, instead of running away from engagement, you deploy digital technologies to do the negotiations. And what's interesting about it is that when these negotiations happen, there is a power structure involved, and digital tools have the ability to dissolve these power structures, and which can lead to new outcomes. So this is the digital capability that is used to facilitate negotiations over very, very politically sensitive topics. And this is where it gets interesting. So as I said, Geodesign Hub is about 7 or 6 years old now. Over the past few years, we have applied these negotiation tools and technologies in various projects. Just some clippings in the case of environmental disasters, infrastructure investment, post-earthquake rehabilitation. How do you rebuild a city after an earthquake? Who decides? How is it decided? Who makes the call? Citizen engagement and so on. The point that I'm trying to make to you is that you have a digital negotiation capability, and it can be applied in different contexts. And essentially what's going on here is that you are enabling structured negotiations. This is not some random thing where everybody shouts or whoever shouts the loudest gets his way, but these are coordinated, structured negotiations that are sort of happen routinely, by the way. Negotiations in these contexts happen every day. You unknowingly do it, trying to influence people, trying to get somebody to get a decision your way and so on. But these happen in personal meetings, perhaps in Excel, or maybe some relationship that you have with some organization or entity. But now you can do it live with new kind of tools to enable this kind of collaborative thinking. And essentially, just to sort of give you a little bit more about Geodesign Hub, it is focused on generation of consensus and agreement. I'm not going to talk about what Geodesign Hub does, but the goal is to develop this consensus. And this consensus is developed in the case of political conflict, social conflict, contested sites, and setting up complex negotiations. And so my point that I'm trying to make to you is that if GIS provides you with the analytical tools for these, geodesign provides you with the social and the political tools for this. And when you combine them together, it gets really, really powerful and interesting. Just some examples. You can have 2 or single issue disputes. What happens to the road? What happens to this park? Do we build a shopping mall or do we leave it as a park? Who decides? How do you decide? It could be 2 or multi-party conflicts. The shopkeepers don't like the transport company, and the transport system has sort of a touchy relationship with the housing department or the city. These are different stakeholders having different problems with each other. Sometimes parties are willing. I'm willing to negotiate, but I don't know how to talk to somebody. It is sort of very routine to have a Ministry of Housing never talking to Ministry of Roads ever, because they simply have never done so. And so then that's why you get some of these problems that you have. Many cases we are used it for preventive measures for a last minute sort of litigation and so on. So when you have this massive project and everything looks great on paper, you try to sell it to the people, and then litigation starts and it's all down to zero. So this is a way to de-risk your implementation. You bring the risks down of litigation and conflict. And of course, what it gives you, which is very important, is the capacity to understand how decisions are made, how political decisions are made. Not an analytical decision, but a political one. And then, of course, there's digital records and so on. And these meetings are not very sort of strange, or this would be any other meeting that you might be familiar with, a charrette or sort of this kind of a meeting. But instead of just having these conversations, people are now using digital tools, just like you would Zoom to conduct an online meeting. You can do it in the same room. We worked all over the world in different rooms, online, and so on. And as I said to you, these are coordinated meetings. So the easiest way to think about this is you're using Google Docs to run a meeting, or a specific way to run a meeting. As I said to you, we have worked everywhere. There is case studies and so on. I can send all of that to you. What I want to do now is try to talk about what happens in these meetings and what kind of open tools we are building to support that. As Kevin sort of has mentioned, how the city grows, or accessibility, is a very important consideration. And the decision to do something or to not do something is a combination of analytical tools and some decision making that you need to have some goal to understand. My accessibility is X and I want it to be X plus 1 or Y plus 1 or something like that. And this is the kind of the domain we are about. And these negotiations look like this. How should a city grow? Well, you could grow over here on the east side, or the south side, or the north side, or improve indicators on this area or that area. And these are the negotiations that they go through in the workshop. So this figure gives you an idea of how this design evolves and how decision evolves around it. So a few years ago, we worked on Basel. Now, Basel is an interesting case because it straddles three countries: Germany, Switzerland, and France. So the Basel agglomeration is three different administrative entities. Of course, as you can imagine, one country never talks to the other country because it is simply not a thing to do. And what they were trying to do, this was worked with the Swiss government, the federal government, is to figure out where Basel will continue to grow. That was the kind of the work. And they're expecting maybe 200,000 people coming into Basel over the next 15 years, 20 years. And they wanted to figure out where would Basel grow. So they organized these events of negotiations where they were like, let's try to figure out where it will grow. They came up with a low spread scenario and a high spread scenario. So if you allow a lot of single family housing, if you allow a lot of kind of the yellow is single family housing, and the darker colors are more denser sort of neighborhoods. So if you say, well, if we allow more dense neighborhoods, then that would be the pattern. And if you allow just a lot of more single family and car dependent, that would be the pattern. Now, the first thing you can see here is that instead of this complex question of how could Basel grow, you have a very specific spatial and a digital way to understand how exactly would it grow. And this is not done by some model or some AI or something like that. It is done by the chief planners and the chief sort of architects of these cities, right? So there is a credibility beyond AI around it. And essentially, that's Basel. And historically, we have open data now. The global human settlements layer has demonstrated how it has grown every 5 years. So this is the GSSL database. Basel's footprint was this in 1975, and 2014 it was that. The white is basically the built-up area, and the black is the non-built-up area. That's what happened so far. Now we also have where it could most likely go in 2040. And what you're going to see now is how do you build this analytical backbone of understanding how this growth will happen. So that is a very specific term called weighted urban proliferation. And so this is the crux of the model. You look at the built-up area, past and projected. You look at the degree of urban dispersion, where people are living, and then you sort of do this kind of computation to calculate the weighted urban proliferation. What that gives you is an indicator of sprawl, essentially. And that's interesting because then you can start to think about where do you want to go. So just like you go to a doctor, he may prescribe a blood test to say, your blood sugar is X, you need to go to Y, and here's what you need to do to do that. And so this was the kind of the thinking behind this, where if you want to prevent a scenario like this, you need to understand where you are now and then try to develop some goals around where you want to be in the future. And so this is the basic sort of mechanism where you say, every year we're going to track my weight or my blood sugar and so on. So this is what it is. The two scenarios were fed into the model. Here you can see the high spread and the low spread scenario. So this is the future human settlements layer, let's say. And then we have a QGIS plugin. Basically, there is a vector boundary, employee count, settlement area, the raster of the built-up area, the vector of boundaries, the output, and then you run it. Basically, at that time, it was a QGIS plugin which takes these data and then produces an indicator. And essentially, what you have now is not only the past, but an indicator for the future to understand where you're going with this. And of course, as with any sort of good industrialization process, now there is a web service. So if you look at the urban sprawl calculation service, this is all open data. So okay, it's okay. That's fine. Is that okay?
That's okay.
Yeah. So I won't click on it, but basically there is an open API, and then there is a GitHub link. That's what it's going to show you, where it takes the exact same thing, but runs it as a web service. So what the crux of the work is to take the QGIS plugin and then convert it into a web service and an API. So you can do this at an industrial level without having to load it into QGIS and click on it and so on. And so essentially, we built that, and that was what I'm going to show you. It's on GitHub. You can take a look at it. And then to test the industrialization, we started to think in a bigger way. And the work that we did was with India. They have an index called Ease of Living in the 100 Smart Cities program that they have there. The idea was to build up a raster data set for 20 years using the GHSL layer, and then prepare resident count and the employment count for these cities using census data. So the two outputs are building up the rasters and then the resident and the employment count. All the problems you would expect with any sort of data like this. What does a boundary mean? Do we take the census data? The city, what is Dublin? Is it Dublin City Council? Is it Dún Laoghaire? Is it Rathdown? How do you define Dublin's boundaries? All these issues. Dublin's boundaries were defined, 100, 200 years ago, when Dublin was a totally different place. And now, what is Dublin? So it's the same kind of issues. Imagery is this, that's the classified imagery. There's the census boundaries. Other problems, including census hasn't been conducted in the last 10 years and so on. So you have to sort of go through this data preparation work where we started to see, well, what is the sub-district boundary and so on. So all of this work that you can imagine with any geo toolbox that you have to do. But you prepare this. I can talk about how this was done and so on. But the idea there being basically you take the GHSL files, combine it with the boundaries, clip it to the boundaries, and then produce the built-up raster. That's the thing that we want, basically. And these are worldwide kind of data sets, so you can bring it for the world. Just to give you an understanding, there is literature between 1990 and 2014. Sprawl grew by 1.2 square kilometers every hour in the world. I mean, that's how crazy some of this stuff is. And directly impacts the 15-minute city, zero net zero kind of goals, transport goals, and so on. So this is a really big problem. And of course, we can do it for the entire country. So essentially what we now have is essentially at a 250-meter level, a data set that we are ready to test at an industrial scale for using the web service, which can be now deployed on Amazon AWS. And you can do this in like a basically very fast. And we haven't done the deployment yet, but it's at the testing phase. And then essentially all the other issues of population estimation and so on, the model requires some understanding of how many people are going to come. You need a geodesign exercise to understand and negotiate where do you think most likely they will go, and then you can calculate the sprawl. And what we're looking for now is just expanding this and testing this out. And so if you have students or colleagues who might be interested in doing this as a master's thesis or some kind of a work, we can do internships, whatever else you want to do. We are in Dublin, so this will continue. But that's sort of the idea, where you build the analytical backbone of these indicators, which are totally open, and then you start to think about these decision-making in an analytical fashion. I mean, it is shocking, but oftentimes people make these decisions without understanding the baseline. So there is a real need to develop a scientific rigor and discipline in these decision-making, because if you don't, you end up in a situation where we are now, which is an hour, 1.2 square kilometers of sprawl every hour. And you can say, well, so what? But the point is that if you continue to do that, there is no way you will meet your net zero or any goals that you set. And I don't have to say it, every indicator on climate change, every indicator on biodiversity loss, is all failing because of this non-scientific way of thinking about these things. And it's all political or it's all random. And that's sort of the real problem that is being solved here. Thank you.
Very much, Richard, for your presentation. Open for questions. I have a quick question. Richard, maybe could you elaborate a little bit on the WPS that you're developing? So specifically around the technologies, and it's based on the OCC standard.
Yeah. So I would like to click it. Can I click it?
I did the clicking.
Basically, it's a QGIS plugin. And what the problem was, the QGIS plugin has been developed by Institute of High Performance Computing or something like that in Switzerland. And what we did was loading all the data and doing all the work in QGIS was...
That link there.
Yes, yeah, and the one below as well. Was very, very time consuming. So then the decision was made that we break the QGIS dependency, which means that you have to conduct an operation in Python where you say all the parts that have a QGIS dependency, you remove them. And then you basically go to the kind of build a new interface, essentially. So that's the urban. Just scroll down. If you just go down there, yeah. So this is the thing. This is the requesting party. You send the vector boundary for what you're trying to do, and then it gets the request. So if you just go to the rendered version.
Yeah, I'm just going to share the screen there for a minute, Rishi.
Just the rendered version. Okay, good. Rendered
Okay.
version. Yeah, that's the API. It's okay.
Yeah.
We just go here. Yeah.
Yeah. There.
Yeah. Perfect. So in the API, you send the resident count in boundary, employment count in boundary, the path of the raster with the built-up area, and then a few other parameters, and then it will do the processing in the backend. So exactly what you would do in QGIS, but without using QGIS. And that's what makes it interesting, because then you deploy it as a web service and use AWS or Google Cloud or whatever else and put some very heavy hardware behind it. And then you just do it at a very fast industrial scale. The opportunity here basically is to then build out an indicator, sort of a PDF and so on, and do it real time. But this is the first step, obviously, in delinking it from QGIS.
And then maybe just one other quick question with respect to the rasters of the built-up areas. Have you maybe looked in Ireland maybe using maybe more localized data sets like Prime 2 or a comparison between the two?
Yeah, so this kind of work has not been done. At the crux of it, basically what you need is a binary raster with one pixel called built up and the other pixel called non-built up. And it's up to you to define what built up means and what non-built up means. We use global human settlements there because it's free, it's available from 74 or something, so you can do some trending. But all of this can be easily configured for the local use. I think a high resolution one would make a difference. I think what's really interesting is this notion of what is the boundary of Ireland or the counties of Ireland. And they were created, I don't know, 100, 200 years ago by a different set of people. And if I were to ask you, what should be the boundary of Dublin in 2050? To prepare Dublin for 2050, how do you do that? How? You can't use the 1800s boundary. You can use natural boundaries, maybe, a river or something. But it's these kind of questions that we need to answer, because if you think that the current organization and the setup is good enough to address these problems, then you're fine. But the reality is that Dublin City Council and the organization of Dublin most likely is not capable to handle the problems that are coming by 2050. And then the question becomes, how do you change it? And it can't be, oh, well, I just think this is the better way or something. And so it's that kind of systematic thinking about the future. These problems are obviously very acute in places like India, where urbanization is very fast and so on. And what does the management of a mega city look like? What should be the boundaries and so on? That's the kind of problems we're answering. How do you really prepare for 2050, not just in like opinions or something like that?
So for a quick question, if not, we'll move on to our next speaker.
Okay. Hi, everybody. My name is Paddy, and today I'm going to be presenting some work that I've been working on in the past year that originally started during my master's in data science. So it's called Radian, and it is a tool written in Python for generating random spatial data sets. So just with kind of a background to why this tool was developed, one of the modules that is taught in Maynooth by Peter is spatial databases. So it's all about SQL, working with spatial data, things like that. And a big thing for classroom assessments or projects or just things in general is having access to good data for that sort of thing. So, as we all know, we have sources like OpenStreetMap, which can be incredibly useful for getting data sets. Having these kind of data sets can be great for, practicing different spatial data techniques like data cleaning, data visualization, data analysis. There's different tools like Mockaroo, I'm sure people are familiar with. QGIS as well has some limited capability that I'll go to in a little bit. But basically the aim was to make this tool that would just make it easier to create these data sets that could be used for classroom settings. So Radian, now the name, as I've been told by some of my colleagues, is a bit of a reach for the acronym, but Radian stands for Random Spatial Data Generator. Originated from my master's thesis, supervised by Peter. And the aim was that it would generate data sets that look realistic. Now, obviously, that's quite a subjective term. I'll go into what we kind of defined as realistic in a little bit. But we wanted to generate these data sets, have them be available in GeoJSON and SQL formats, just so you can throw them into QGIS or throw them onto a PostgreSQL database and generate them quickly. And just from the literature review, it's found that exercises that are interactive, interesting and relevant to students, help encourage engagement. So being able to create data sets that maybe mimic data from their own country or data to things that are more specific to them can just help bring that engagement. So a quick look on just some background work. Some packages already exist for creating random data. The GRD package in SPSS and R allows for this, and there's some work there just on specifying real-looking synthetic data by giving some different properties to the data set. But there was kind of a gap in terms of generating spatial data sets. I already mentioned that QGIS, as I'm sure everyone is aware of here, is capable of doing. So QGIS obviously is an open source GIS visualization and analysis tool, and it can generate random points in polygons under the shapes, given some kind of shape. These points are very uniformly distributed throughout the polygon. They don't give you any options for extra metadata. You kind of have to do that yourself with some post-processing. They do have a primary key, but again, that's kind of limited in its utility in terms of, again, classroom examples if you want to use real-looking data. So some pros and cons. Obviously, it's very fast. It is able to generate large data sets like that, easy to use, and there's a variety of formats and projections that QGIS can export to. But like I said, there's not many options for metadata, and the distribution is a little bit unrealistic. Again, I'm using that very vague term that can be depending on what your context is for that particular distribution being realistic. So on that point, if we were to look at these two data sets, so the one on the right is a real set of data pulled from OpenStreetMap. It's, I believe, a collection of fast food restaurants, and that is Glasgow. So on the left then is a fake data set created with QGIS. Now, if we think about what makes one of these look inherently real or inherently fake, well, I've told you that it's the real data set is a set of fast food restaurants. So, you know, you can think reasonably that something like that will be quite concentrated towards the center of an urban area like Glasgow. But at the same time, fast food restaurants are quite ubiquitous. They could be anywhere in a given sort of area. So what's to say that this kind of open, more spread out distribution is unrealistic? Or say if not knowing what the data represented, say if it was traffic lights or something like that, well, then this distribution does become a little bit more realistic looking in that context. So just a quick look at some of the packages that we used for this. Obviously all open source. GeoPandas was one of the main. GeoPandas and Shapely were sort of the two main drivers for dealing with a lot of that spatial data. And there was a little bit of scikit-learn just for some of the segmentation we'll look into later. And of course, random, NumPy, and matplotlib for any plotting. So I'll try to just go through this quickly, just to not to delay too much, because I'm sure we all want lunch. So generate random points in a polygon. There's a few different ways that you can do this. And obviously, if we have a given region and we want to generate a point in that region, the simplest way to do that is, again, this original presentation was in Glasgow, hence all the Glasgow related imagery. So if we get a bounding box of a given region, well, that bounding box is well defined by 4 different points. So if we want to generate a point in that region, we can, as you can see from the little Python snippet there, if you generate a point with the X and Y values somewhere within those ranges, then you can do a bit of a check to see that that point is both in that bounding box and also in the actual polygon, and then you have your data set. So what was kind of found in the sort of iteration of this project was initially what we would do is we would generate a point, check if that was in the polygon, then decide whether to add it to the data set or not. But when you're doing these points and polygon checks over and over again, that really just adds up to a lot of computation. So we found was the kind of scattershot approach where we just initially use the bounding box and we generate more points than needed. I can't remember the exact ratio offhand, but let's say we want 1,000 points. We generate 2,000 points, but we generate them in the bounding box. Roughly speaking, it'll depend on the sort of area of the polygon. I think the ratio is about 50-50 between the polygon and the bounding box. So what you can do is you can just take away, you can do one spatial join that will check to see if these points are outside the box. because it's a lot quicker to just do one big spatial join than all of those small ones. And then you get rid of those excess points, and you're left with just a set of data points inside the polygon. So now that's if you're just wanting to generate uniform points. And again, just a note on looking at the fake data. One of the things that Radian does not take into account is actual land use or things like that. It kind of just takes in a given polygon and runs on the assumption that it's all usable land. So obviously, if there's a chip shop that is in the middle of a river in Glasgow, I don't think you would want it to be going to that anytime soon. So as I mentioned earlier, the context is important when we say if data is realistic or not. So a uniform distribution, depending on what the spatial phenomena is, could be realistic. But for other things, like I said, maybe houses or restaurants or pubs or whatever, could have a more kind of centralized distribution depending on where you are. So how we try to mimic this kind of radial distribution, what we call it, is so like the example of the real data earlier on, we saw that for an area like Glasgow, points were centered towards the sort of urban center. And as the further you go away from that center, the density goes down. So a simple way of mimicking this is by splitting up the region into, initially anyway, these circular buffers. So these are all just concentric circles. And what we would do is, so there's 5 regions here. Let's say we have 1,000 points that we want to generate. If we put 200 points in each of these circles, well, what happens is because they're layered over each other, you get 200 points here. So they'll just be around here. Then you go on to the next circle and you generate 200 points there. Well, obviously they're going to cover this area, but they'll also cover the area of that original circle. But this density will be a little bit more spread out because it's in a larger region. So that keeps happening. Each of those regions have 200 points, but because of that overlap, you end up naturally getting that kind of concentration towards the center, whereas in the outer regions, that density goes down a bit. So as seen from some of the real data, that kind of distribution really pops up a lot when you're looking at OpenStreetMap or different data sets. So that was the best sort of distribution to sort of mimic for Radian. And then going into, well, okay, we can distribute points that way, but let's say we want to mimic different districts in an area or boroughs or things like that. Then we have to break up our given polygon into smaller polygons. So with that, bring the Voronoi polygons, or Voronoi. I've never actually heard it pronounced. I've only ever seen it written down, so apologies if I'm saying the wrong one. But Voronoi polygons are a partitioning of a plane given endpoints where exactly, so a set of generating points, so there's 20 points in this case. So each Voronoi polygon contains exactly one generating point. And every point in a given polygon is closer to its generating point than any other. So basically, we have 20 points. This will give us 20 regions. So for the case of Radian, if, say, we want to have, so this is for part of the generation, but I say we want, for argument's sake, 128 different regions in a given polygon. Well, we put those points in, and our algorithm does a bit of messing around with k-means clustering by generating a big set of uniform points, getting some, running that clustering algorithm, getting those centroids, throwing that into the Voronoi, and then we get these nice little polygons. And what we do then is, you can see from the coloring and the subsequent join of those regions, is we, so they're colored by their distance to the center, and we end up with what I mentioned before with that radial distribution with those concentric circles. But instead of being super uniform and being in those circles, the shape is actually much more influenced by the actual overall shape of the input polygon. And another step for Radian is this idea of primary and secondary generation. So when I say primary generation, it's at the kind of macro scale, so at the scale of the whole input polygon. And then secondary is at this more localized sort of borough or ward level. So this allows us to get a bit more of a, again, varied distribution, because naturally, if you have an area like Glasgow or an area like London where it's split up into specific districts or wards, you're obviously going to get some kind of spatial patterns appearing at that sort of district level, as well as the macro, overall level. So this lets us sort of mimic some of those behaviors in the outputted data set. And just this shows a little example of what's called the moving centroid. So rather than just using the real centroid of a given polygon, to make it again appear a bit more realistic, if we think of examples of, say, Boston or Tokyo, where the sort of center might have originated around the docklands or the port. So the kind of metropolitan area might be closer to, say, the east or the west. Radian is able to generate a moving centroid kind of around sort of an elliptical region around the true center to, again, add a little bit more variation. So everything gets shifted over a little bit more, just again to add a bit more diversity, a bit more variation in what you can get. So another thing then in terms of wanting these data sets to be realistic is having metadata. So again, particularly for a classroom setting, if you want to give class a data set, and have them test out, say, SQL queries or spatial joins or things like that, it's a bit more immersive to have data that is actually seems to represent something real. So in this case, if we wanted to generate a data set of fake fast food restaurants, Radian lets you do that. So how Radian is controlled is through a simple JSON parameter file. So there's just a list of various parameters that control how it's generated. So the number of points, the ratio between the primary and secondary points, the number of secondary regions you want to generate, and then variables for this additional metadata. So you can have timestamps, you can have ints, and you can also include CSV files with strings or other values that can also have, now it's optional, but you can include a weight. So this CSV I have here, I think actually I initially pulled it from London, from OpenStreetMap. So it was a list of the names of fast food restaurants in London, and the weight, according weight, was how often it would pop up. So what this lets me do is put it into Radian, and each point that it generates will be given the name of a fast food restaurant. And because it's following this CSV file, that distribution will, again, mimic a real kind of distribution. So in this case, Pret a Manger, Subway, McDonald's with top 3. So you'll see those the most often, and it'll start going down like that. But in addition, then each of these has an opening time, a closing time, a phone number, and then obviously the name. So again, this adds a little bit more sort of realism to the data. Can hopefully get that little bit more engagement when using students. And there's just another example. So this data set is fully synthetic, generated by Radian, looking to mimic that real data set of fast food restaurants in Glasgow. And like I said, they all have their own names, phone number, which is just a 10-digit random int, opening time, closing times, and then of course they all have some primary keys. So in terms of use cases for Radian, I already mentioned CI61 spatial databases. So it's been used for that, for either just allowing students to have their own data sets for practice or for generating data for their projects. One of the main assessments in 621 is your geospatial story. So you basically tell a story using spatial data. It can be whatever you want. Yeah, so it gives a useful tool for students and for Peter for generating examples for making these data sets. And as we've seen in the last year or two with ChatGPT, showing the utility of being able to generate these unseen synthetic data quickly. And it's not on the slides, but one of the, this year, my PhD, my sort of, I had a small project before starting placement of just working a bit on Radian and improving it. And one of the things was just improving speed. So it's part of a paper we were working on, doing some comparisons between QGIS and this. And it wasn't, QGIS was generally still beating it out. But in terms of numbers, we were able to get it quite fast, which was good. But that can always be useful in class. So just looking towards the future of Radian, Peter mentioned my placement in Met Éireann, which I'm just finishing up this week. So the current work, or what we've been doing this year in terms of working on Radiant is trying out some different methods of generation. So I've gone through the Veroni method of breaking things up. I've also been looking at using raster grids because it's a lot easier to just generate these squares. And as I mentioned earlier with the bounding box example, it's much easier to just generate a point in a square, especially if you don't have to worry about then doing a join to check if it's in the square. So that's been tested. That we're trying out with that, but obviously it's hard to get shapes that don't look too, robotic and square. In addition, another method is triangulation. So rather than using squares, breaking them up into triangles, because in the same way, it's a bit easier to define the space of a triangle and generate a point in there. Essentially generate a point when you know it's going to be in there and you don't have to keep trying or keep checking that it's in there. And looking for some future work, we want to look at some AI and more machine learning oriented ways of generating these points. So one of the big sort of jumping off points for when we get back to this work in September is GeoPointGAN, which works with generating synthetic spatial data with local label differential privacy. And my placement project has all been on generating synthetic satellite imagery with adversarial networks. So kind of using that experience, now that I have a bit of background in GANs and how to use them, and seeing some examples of what could maybe be done in terms of generating points, that'll kind of be the main direction of trying to get some AI and machine learning and throw it at the problem. So yeah, that's everything. If there's any questions or queries, you can either ask me now or you can get me the email there. And that QR code is just the GISROC 2023 paper when we first submitted this work. But thank you.
Yes, so thank you so much for the presentation. We just go back to the slide with the So recently I've been trying to research on some of the best ways kind of spatially in this space, right? When you look at that, when you're looking at these big squares, it could be maybe about 1 by 1 kilometer, maybe something like that. What I found that is that inherently, if you're trying to kind of have distances from one square to the next one, what you do, you can separate from one square to the next one. Now, if you want to compare the distance, like say if you try to compare the distance between like center one to the next, if you look at the one that are adjacent, then it almost be equidistant. But if you look at say you're looking at the square here and the one at the corner here, so if you look at the distance from the center of this one to the other one, it doesn't normally match. So what some other people are doing is the thing I got from you guys that they're looking at something they call hexagons. Okay, and that's kind of giving them a much more better way to kind of split space. I think they're using that in terms of the pricing and the rest of the pricing. But there's something also exploring in terms of how to generate
Yeah, so that's definitely something that, because one of the things with because I found in particular with generating the squares and that raster grid, it's much easier than generating, say, the triangles, just because at least some of the methods I know there's, I think it's in either in Shapely or GeoPandas is like a triangulate method. That it was harder to get the kind of uniform sort of space that you have there, where it's just, all the squares are equal, whereas the triangles would be a lot more messy. Whereas, yeah, with the hexagons, obviously you can tile the full plane with those, and it probably gives a little, I guess it would probably give it, with just using the squares, you end up having that kind of boxy kind of nature depending on how big they are. Whereas with the hexagon, you kind of have the mix of, you have those edges of the triangles, so you probably get a little bit more kind of resolution in terms of breaking up the space. But then as well, because they all, they're all very uniform and can join together, it's probably a good way of going. But that's definitely something that I'd be interested to look into for sure. Okay, yeah, cool. Thanks.
Question here, Mike?
Yeah, sure. Thanks, Paddy. Yeah, great. I guess kind of one of my questions was going to be kind of linking to that environmental context that you said that I kind of link my last restaurant into a river and thinking about the future in terms of really what people might use this data for. So you do a lot of linking with various and that. So what some of your strategies might be to deal with that.
Yeah, so it was one of the, actually came to me during the first talk, because I've actually been, for my placement at Mid-Air, I'm working with Sentinel-2 imagery. So working with a lot of that. And I was actually thinking of, there's different ways you could go about it. So say one of the ideas I had initially was sort of integrating the OpenStreetMap API into it, where you could actually, given a polygon, be pulling in, say, roads and things like that, and actual land use data to have that, influence where you can generate points. I'm going to generate a point here. Oh, no, that's a river. Okay, won't do that there. But because basically the use case of it is we want to just be quick in the classroom, and that was a bit too inefficient just for what we were doing. But on the satellite imagery, what I was actually thinking was that you could even, maybe even using the Maps API or something like that, is use that as a way of, I'm not sure if it'd be faster, it could end up just being slower, but basically using those images to pull up roads or pull up road use or land use or that or something like that to sort of segment the area then into usable areas where you could put the points, and maybe have that as another method of breaking it up into smaller polygons to have those different regions.
Do you follow up?
No, it was more just going to be helping that growing the CSV from London to get the past few trains to go to Glasgow. And there was a study or an article out last month that said that Brexit divide was the real north-south divide. So the UK, so presented this in Glasgow, that might be a question mark.
Cheers.
Yeah, Paddy, really, really good tool, really useful. Particularly in the context, I suppose, of data sensitivities. It's not necessarily personally identifiable information, it's more about the location of assets, that may be sensitive to an organization.
Yeah.
Have you looked or thought even about, instead of, I suppose, associating with points with, the Voronoi polygons, and kind of grouping them there, about using lines instead? Because it would be quite useful for, say, point assets that are associated with line features like roads or rivers, to generate random fake data along those type of features, rather than just within polygons or something.
Yeah, so that was one of the original ideas before kind of settling on the Voronoi polygons, was thinking of even actually before even pulling real roads or getting real rivers or things like that, was actually thinking of ways of how could you generate, say, fake roads, or say an initial idea was even almost kind of similar to the Voronoi, but say generating polygons and then using those using their vertices then as like kind of a network of, oh, these are now fake roads. We'll use those to influence the points and say generate points based on a distance between the roads or things like that. But at the time, then it was just the Voronoi polygon was kind of an easier route to go. But that's definitely something I want to consider, because obviously, both the land use, but I'd say most particularly roads and paths and things like that would be such huge influencers for the distribution of a lot of the points. So getting that kind of functionality would definitely be a wanted feature for it.
I think it'd be really useful in the context that we develop mobile apps that we need to test. So people need to go out on the ground and walk roads, or use them on trains. It's very useful to have fake sample points or data points from those networks.
Yeah, for sure.
Really, really good.
Cool. Cheers. Thank you.
Would there ever be or is there ever a use case where they can have a small data set of points that exist, but they like maybe try to get to this maybe a user what it would look like if the data set was maybe created by synthetic codes? Is there ever a possibility where you could see a small amount of a sample and then say what this one would look like?
So that's not something that's currently there, but it's definitely something that's been in my mind in terms of looking at the sort of AI and machine learning things going forward. Because from, say, working with generative adversarial networks, the kind of idea of a lot of the use cases of those would be, oh, you have a small data set and you want to augment it. the GAN would be able to learn the characteristics of that data and then be able to, produce data that's more like representative of it and that. But I think it would, even just in the current version of Radian, not using too much of the machine learning stuff, that would be a great feature to be able to, give it a kind of data set and even just have it like get averages or, different things like that to expand on that. Because like I say, it would be very useful just in terms of, say you have a data set for a classroom example or something like that, oh, this is really useful, but it's too small. Being able to throw that in and then actually expand that would be, that would be a really good feature.
If you use a GAN to generate these random points, what would be the input? And through because I assume you will use a GAN to create the synthetic satellite imagery, right?
Yeah.
What would you use as the input?
I don't know. I haven't. My work on GANs for my placement was the first time any really dealing with them. So any of my experience has mainly just been working with images as the input. So one potential thing could be that you could feed in, say, a patch from Sentinel or a patch from Google Maps, and maybe the network could learn usable areas that points could go into, or things like that. It's been a while since I've actually read the GeoPoint GAN paper, so I need to refresh that a bit. But what it would basically do, I believe the inputs would essentially be full data sets, and what it would do is it would create a point data set, but the points would be sort of anonymized. So yeah, that differential privacy. So yeah, that's something that I'm still kind of trying to figure out. I guess an idea could be, in the same way with a lot of the GANs, for when it generates, say, images, the actual input for that is just random noise. So it could be a case of getting real input data, say real data from OpenStreetMap, training it on that, and then it would be able to train it on that with the idea then that your actual input would just be that random noise vector, and then it would create that data set in the end. But yeah, still an open thing I need to look into.
Thank you very much, Paddy.
Cheers.